So the next thing you need to look at in question 5.4 is the modeling of an SN1 reaction. So just to refresh your memory a bit from CMY 284, an SN1 reaction or substitution reaction, so it's a substitution reaction. And what it entails is you have some sort of carbon backbone which is connected to a leaving group, Y, and the leaving group leaves. Surprise, right? Which forms a carbocation intermediate, which is then attacked by a stronger nucleophile than what the Y is a leaving group, or than what Y minus is as a nucleophile. Because remember, technically you have Y minus here still. So in other words, the nucleophile and Y minus is competing to attack this carbocation intermediate. Now, whichever one wins forms the product. In this case, the nucleophile is the stronger nucleophile. This one is stronger than the Y minus nucleophile. And then you form some racemic mixture of products with Y as a product as well. So, okay. Remember, this is technically not balanced, and the reason it looks like this is because here at the beginning you have nu minus plus, so that thing plus nu minus. There's a bit of ambiguity in my reaction mechanism, but I'm quite sure you are capable of figuring out what needs to be where. So just make sure that your charges are balanced. So we have minus here, there needs to be an extra minus here, which is the Y minus, and here needs to be an extra minus, the nucleophile minus. Okay, so keep this in mind. Then if you generally looked at the potential energy diagram for an SN1 reaction, this is what you would see. So we'd first see a first activation energy for the dissociation of the Y group, the leaving group, which leads to your carbocation intermediate, which is then attacked by the nucleophile, which has a transition state of R sort of bonded to the nucleophile. That's what the dash bonds are versus the solid bonds. And then that forms the product. As that bond shortens, or that distance shortens, it becomes an actual chemical interaction, and you're left with your leaving group. But unfortunately, beta-mol-cal can't model this well, or at least it's going to be very tricky. So what I've decided for you to do, but you can still enjoy what it does, is I want you to model it as follows. So you're going to clump this part together. You're going to draw a potential energy diagram for me with your reagents. So in other words, remember how you're going to get this starting energy. Remember, you can sum the energies of reagents. Okay. Then you have what I call a transition composition. So what does the transition composition entail? Okay, so the first hint is going to entail this carbocation intermediate. So it's definitely going to have that. Now remember, you need to keep all the other components, sum their energy, you get to this point. And you also have products. Then you need to look at the activation energy. You need to look at endothermic versus exothermic. I think you know how to do that. And you also need to argue in which direction is this reaction going to take place. I'll leave that up to you, because there's a specific one. So you're looking at substitution of a chloropropanol to an iodopropanol. So in other words, the leaving group is chlorine and the nucleophile is iodine. And you just need to figure out from the energetics what's going to happen. You can also look at the orbitals. You're more than welcome. You know, be expansive. You have the time. It takes 2 seconds to calculate anything on beta-mol-calc. So use some time. The only thing I want to ask you, so I have left it up to you. It says energy. Just which energy are you considering? All those ones. Are you considering enthalpy? Are you considering entropy? Are you considering Gibbs free energy? You need to make a decision. So you can compare your reagents with what is called the transitional composition. So that's why it's not a complex or a state. I call it transition composition because it's technically a composition of a bunch of things. And your product. Compare them, draw a nice diagram. You can use Excel. You're just going to have to connect the lines yourself. Yeah, and I'll have to see what you come up with. So it should be straightforward. I think I've given enough. Remember what we did in the methane example in terms of summing the energies. So I look forward to see what you come up with.